Nobody tells you the real reason you need data structures and algorithms. It's not a rule some professor made up. It's physics, and it's baked into every chip in your computer. Physically, RAM is a massive grid of mailboxes. Your CPU can grab any address it wants. But compared to how fast the CPU can think, fetching from RAM is agonizingly slow. To survive that gap, CPUs keep tiny, ultra-fast onboard memories close by, L1, L2, and L3 cache. The whole game of writing fast code is keeping the CPU fed from cache instead of waiting on RAM. When the CPU fetches one item from an array, it doesn't grab just that item. It grabs the whole neighboring block and loads it into L1 cache, betting you'll need the next one soon. Because an array stores its data side by side in memory, that bet pays off almost every time. A linked list scatters its data all over RAM, with each item pointing to the next. The CPU can't predict where the next one lives, so it suffers a cache miss on almost every single hop, jumping back out to slow RAM again and again. That's the real reason you reach for an array over a linked list, not because a textbook said so, but because you understand how the CPU's cache lines actually work. Every instruction your CPU runs costs time and real electricity. A 3.5 GHz chip is burning through 3.5 billion clock cycles a second, and every wasted one adds up. Say you've got a million sorted names and need to find one. Check them one by one, linear search, and you might need a million steps. Cut the list in half each time, binary search, and you find it in 20. Now scale that to billions of users hitting Google or Amazon. Choosing the right algorithm isn't academic. It's the difference between server farms burning millions of extra dollars in power and cooling or not. This same physics doesn't just shape which data structure you pick. It shapes how entire programming languages are built. Take C and Rust. Both give you raw control over memory, but they made very different bets. C is a thin wrapper over the hardware. Its arrays don't even know their own size. Read past the end, and C will happily hand you whatever garbage sits in that memory address. Rust gives you that same hardware-level layout, but its arrays carry their length as part of the type. Try to read out of bounds, and Rust halts safely instead of reading corrupted memory. To really see the difference, let's build the same thing in both languages, a user that holds an ID and a location point. In Rust, the point lives directly inside the user, one flat, contiguous 12-byte block. The CPU pulls the whole thing into L1 cache in a single clock cycle. In Java, user doesn't hold the point. It holds a pointer to it, sitting somewhere else entirely on the heap. And both objects pay a hidden tax, a 12-byte header just for bookkeeping. Reading the location means the CPU stalls, jumps across RAM, and pays for a cache miss. Same data, same two integers. Rust, 12 bytes. Java, 40 to 44. Java spends over half its memory just on bookkeeping. Why? Back in 1995, Java's creators wanted memory management taken completely out of the programmer's hands. That meant a background garbage collector had to track everything. And for a GC to safely sweep objects, every object needs to look and behave the same way. Uniform pointers made that possible. Rust, in the 2010s, wanted that same safety without paying the performance tax. Its answer: check ownership at compile time. The compiler already knows exactly when a user and its point are born and destroyed together, so it can safely pack them into one block, no garbage collector required. C gave you flat memory, but zero safety. Java gave you safety, but paid for it with pointers and a garbage collector. Rust found a third way: full safety, checked before your program even runs, with the same flat layout as C. Once you've actually seen memory laid out like this, physically, byte by byte, data structures stop being rules you memorized for an interview. They become engineering decisions you understand from the ground up. If you want to go even deeper into what's happening inside your machine, that's next.